Good morning, ladies and gentlemen. Today I'm going to be talking about Newton's laws of motion. It's April 5th, 2020. There are three. So during the motion lab as well as the marble lab as well, we've kind of learned about some of Newton's laws of motion, but we really haven't stated exactly what they are. And so one of these is that an object in motion stays in motion unless it's acted on by an outside force. When we were doing the marble activity, we noticed that the marble just continues to roll, and so we put something down that would block it, and so it was acted on by another force. When it ran into that book, it collided and went backwards. Number two, an object at rest stays at rest until acted on by an outside force. So if that marble was sitting on the floor, it would just chill until something came along and bumped it or pushed it or whatever. And then number three, objects in motion move in a straight path unless they are acted on by outside forces. So again, coming back to that marble, when it rolled down the track and it hit the book at the end, um, we noticed that like it bounced off and went backwards the other way, so it was acted on by another force. So we're going to go through Newton's three laws of motion. These are not quite it. They're a little bit different, worded, and I'll talk about that in a sec. But so this is kind of the introduction for that. So the first one is the law of inertia. So basically, an object at rest, it resists, or excuse me, an object resists changing its motion. So if we look at this dude chilling in this cart here, we have this dog who's thinking about a cat. Um, the person that's sitting on this what's it called wagon, when that wagon gets pulled by the dog, the person tends to resist any of changing in its motion, and so you notice that the guy just kind of like falls out of his cart and then says stays at rest. So like an objects try to either stay in motion or they try to stay out of motion. It's one of those two. And so if something is moving, it's going to try to resist changing that motion. And then if something is not moving, it's going to try to resist that change in motion too. Basically, any type of acceleration is going to be resisted by an object. And so that's called inertia. That's the same reason, like in our motion detection lab the other day, why we couldn't get exact corners on our graphs. You can't stop instantly, and you can't go like 0 to like 20 miles an hour instantly. Like there has to be some sort of like gradual buildup or decline of that change because your body's resisting that change in motion. It takes a while for us to accelerate and uh, decelerate, which are technically the same thing, but yeah. So that's the first law. It's the law of inertia. The more massive an object is, the more inertia it's going to have. So, kind of coming back to us walking, as well as just thinking about cars in general. Like a large semi truck is going to have a lot harder time slowing down or speeding up than a like us, a person, right? Like we are less massive, or we have less mass or weight, one of the two, or I guess both. But I'm going to stick with mass here because weight is a little bit different. But we have more mass. No, sorry, we have less mass than a semi truck, and so therefore we can change our direction a lot faster than a semi truck could. And so I guarantee there's been times when you've been riding in a car or riding on a bus or whatever, and you've been behind a slow semi truck as it's been either going from a stop to up to speed or whatever. And I'm going to assume that whoever was driving that car or in the bus or whatever vehicle you're in probably tried to pass the truck because they were taking a long time to get up to their speed. And so it took a little bit of time. People probably got a little bit annoyed by that slow speed. Um, so the more massive an object, the more inertia, or the longer it takes for that object to get up to speed. The less mass an object has, the less inertia it has. Basically means that it can change its speed relatively quickly. Newton's second law of motion, it's best described as this equation. So force times mass equals, or excuse me, force is equal to mass times the acceleration of an object. And so if you apply force to a mass, so anything has mass, right? Like if I think of a my office chair, it has wheels on the bottom of it, but it does have mass. So if I were to apply a force to it and push that chair, it would accelerate. It would speed up to a certain speed, and then it would go at a constant speed. But once I stop pushing on it, friction kind of takes over and slows it down. In a perfect world where there is no friction, if I were to push on uh, that chair, if I were to push on that chair, it would accelerate and it would be, and then it would go to a single speed. So once my fingers left it and I'm done pushing it, that speed is the speed that it would move at constantly, where that velocity would be constant once I'm done applying a force to it. So you can only accelerate when there is a force being applied to a mass. So that's Newton's second law. Again, we can use these triangle things to kind of help us with calculations. And so since force is equal to mass times acceleration, that puts the F up at the top of the triangle. And then you have mass times acceleration down on the bottom. And then you could just plug and chug numbers from that. And so to kind of help us with this, there's a little problem in the next couple slides that I'll talk about. But so if you apply a larger force to a soccer ball, it'll accelerate at a faster rate. If you apply a smaller force to that ball, it will accelerate at a slower rate. So for instance, if I had two soccer balls next to each other, one I come up and boot as hard as I can, it's gonna fly like pretty far. It's gonna be going pretty quick. It'll accelerate really fast, and then it'll land pretty far away, right? If I apply a smaller force, let's say I just tap it with my foot like I'm doing a dribble or something, I just tap in my foot, it's gonna accelerate at a much slower rate. It's still gonna move, but it's not gonna move very fast, and it's gonna just kinda, like, move a couple maybe a foot in front of me or something like that. And so, as we increase the force, the acceleration increases as well. Um, and so you could also change the masses as well. So, and if I have a small mass, let's say like a small marble, um, it will accelerate much faster than a large marble or a larger mass, because as things gain more mass, they have more inertia, which resists that motion, and so it'll take them a long, or they'll have a slower acceleration to get up to speed. So you can see here, if we have a really small mass like that, and we apply the same force to both objects, it'll have a larger acceleration than if we had something that was a little bit more massive or heavier, which would have a smaller acceleration. And so here's this problem. So we push a ball with a mass of 5 kilograms. The first time we push with a force of 10 newtons, and the second time we push with a force of 20 newtons. What will the rate of acceleration be for the ball in each of these cases? So if I flip back a couple slides to this triangle, the force in the first one was 10, and so I could create a new triangle like this, and I put in for force, I put 10 newtons. The mass was 5 kilograms, and then I'm trying to find acceleration, so the A would still be in that triangle. And so I would take the force and divide it by the mass, and so it's 10 newtons divided by 5 kilograms, and that gives me an acceleration of 2 meters per second, or 2 meters squared. Uh, if I were to apply a force of 20 newtons, um, it uh, it would be 20 newtons right here divided by 5 kilograms, which is equal to 4 meters per second, or 4 meters per second squared, which is my acceleration there. And so I just basically plug all of that into my triangle and uh, solve from that. Okay, so now suppose that you use the force of 10 newtons to hit two different balls. So we're using the same force this time. one has a mass of 5 kilograms and the other has a mass of 2 kilograms. What is the rate of acceleration for each of these balls? So I'm going to again go back to my triangle. I notice that I have a force of 10 newtons and I have a mass of 5 kilograms. And so if I come back to that triangle, the force of 10 newtons, a mass of 5 kilograms, that's going to give me an acceleration of 10 divided by 5, which is an acceleration of 2 meters per second squared. So that's going to be my first acceleration of the ball. And then the second ball is at 2 kilograms. So I'm going to take 10, which was my force, and I'm going to divide it by 2, which was my mass, and that's going to give me an acceleration or rate of acceleration of 5 meters per second. And so the second ball, the one that is smaller, even though it has the same or the same force being applied to it, has a much faster acceleration because it has less inertia. The third Newton, or the Newton's third law of motion, is that for every force there is an equal and opposite reaction force or opposite force. So, for example, in this comic here, you see that this dude is turning on this water feature. He has his hose ready. When he sprays it, the hose pushes him back, and it also pushes forward onto the plant. And so then he gives this one-liner. But this applies really well back to our marble activity, where that ball or the marble that rolled down, when it hits the books, it's applying a force on the books, but obviously the books are much heavier than the marble, and so they both push on a force, or they both exert a force that is equal to each other. And so the marble is pushing on the books, but the books are pushing back on the marble. And so you see that the marble actually got pushed back and kind of reflected back onto or into the track because of Newton's third law of motion. This also applies if you've ever pushed somebody in a car. So in the winter, someone was stuck, so I had to get out and help push them up the hill on Stang in Ontario. And so I had to get out of my car. I was pushing on the back of this car, but the car was also pushing on me. If the car wasn't pushing on me, then I would be moving forward through the car. But since we both had opposite forces, we were both stationary there. If I push harder on the car and my force arrow gets bigger, the car is also going to push back a little bit bigger, but I'll have a better chance of moving um, the car itself. And then so lastly, let's do this Kahoot. I have opened it up so you could do it on your own. Um, and that we're just going to review those three laws. So that's our last part. If you have questions, let me know. I'd be happy to help you out.